around Memorial Day. The reason it's done at MDRS is because of the lovely Mars analog background. This is a picture of near MDRS with Factory Butte in the background that was taken from the second site, the engineering site. So we hold it at MDRS, and then every year we change the competition. Well, not quite every year. Every year the competitors can accomplish the task, we change the competition. Okay? So next year we're going to make some changes because people have finally gotten the sample return task down after about 4 years of having it. So it includes both new and old teams. So the new teams, basically the first year they come, they don't always do as well as the old teams because their batteries die and they're not used to the harsh environment of the high desert of Utah. So generally the returning teams do a little bit better. However, we have had some exceptions where the first time a team has competed, they've placed, and York University is one of those teams. Okay. So as I said, the backgrounds changed once the teams accomplished the task. The first year we had just 2 teams enter, UN Reno and Brigham Young University, and it was just a soils competition and like a fluorescence extremophile. So they had to tell the difference between the coloration on the rock, whether it was biological or mineral. And that was, we asked them to do it via optics, so that's a camera, or via some type of spectrometer. So ever since the beginning, most of these rovers have been highly equipped with spectrometers or pH sensors or some type of in situ science measurements. The first year we did geology and soils. The second year we did extremophiles. And the third year on, we've done site survey and sample return task. This year is the first year that the majority of the teams could actually accomplish the sample return task, so we'll be changing that. It's also the first year that they could accomplish the site survey task. We'll be changing that one as well. The engineering tasks have to do with navigation and transport and delivery of cargo. So basically you have to take a container off your rover, deliver it to a location, pick it up from the location, a different package, and put it back on your rover. You may think this is easy, but a lot of robotic arms, they have to manage the weight, etc., and not have the rover tip over, and there's a lot of different challenges with it. The other thing they've had to do is press buttons like switches or plug in an outlet, etc., and screw nuts and bolts like you would have to fix a rover in the field. And this year we've added the cleaning the solar panel task because that is an issue on the surface of Mars. Okay, so this year we had 5 teams. We originally had 10, but half of them were not able to make it to Utah for various reasons. So we actually only had 5 in the competition. Brigham Young, who has been in the competition since the very beginning. They're the only team that has been in the competition since the beginning. Cornell, which this is their their first year to ever compete. University of Michigan, which I believe this is their 3rd year. Scorpio, which is the Polish team that it's their 2nd year, but it's their 2nd or 3rd year to compete, with some of the team members being on their original Magma team 3 years ago. And then York, which is their 5th competition. Okay, so the first team, BYU. Brigham Young is one of the closest universities to URC, and so they've competed every year. They've had various evolution designs in their rover, but they've always had a lot of creativity and ingenuity when they design their rovers, and they use simple but effective tasks. I should also mention that the budget for these teams range. Like, I know some teams get maybe like $1,000 from their university, others get like $10,000 from their university. So they have a very wide range of support in both money, faculty, and resources from their university. BYU has tons of faculty support, not as much money support. Most of these teams also come from the engineering departments, but they also have to have science on them. And in BYU's particular case, they have a science faculty advisor, but the team are engineers. So the science department wonders why they have to pay for it when the students are engineers, and the engineering department wonders why they have to pay for it when the faculty members in science. So that's actually a problem with a lot of the rover teams, but especially at BYU. But their rover this year, they had some really great tires. Worked, it didn't flip over. Some years it flips over, and they have a really great, strong but simple design that is effective and works. So, and BYU placed second this year. Okay, Cornell, this is the first year they've joined the team. They had a really nice, robust rover for their first time in the field. They were going to compete last year, but they didn't, so they knew a lot of the environments and the parameters, and they did a lot of their research prior to coming. So their rover worked the first time, and they actually placed third. This is one of the teams that placed the first time they competed. University of Michigan has really great ideas. They're inflatable tires. These right here, I believe, is a car mat cut off and glued onto the tires. Without this tread, these inflatable tires probably wouldn't go very far. And if you notice, it's kind of coming off right there. The environment can be pretty harsh, but these treads were essential for the navigation and roaming in the science tasks. Okay, Scorpio, this is a Polish team. They had some great maneuvers. They had a spectrometer on their rover. They also had one within their, I think they took it from the rover and brought it to their lab analysis tent for the survey task, which was pretty cool. And I should mention Michigan also had a methane test. It was a very simple Coke bottle they did, and they had a little chemical reaction in it to tell whether or not there was methane in the soil, which I thought that was really nice because their entire experiment maybe cost $1 for the bottle, and they could say if methane was there. So that's the creativity really comes out when the teams don't have the money. Some of the things they do are amazing. Okay, oops, wrong way. Go. And York. York won the competition. Congratulations. This is them in front of the MDRS hab. This is a very robust rover. I don't believe it flipped over any times. I believe it worked in every single task, which this is an accomplishment. Generally, everything works the day before, but when they get out there for the competition, the rovers won't work and won't communicate, and it's pretty much they spend like 30 or 45 minutes trying to get their rover to work as much as it did the day before. So York, their rover worked great. They accomplished all their tasks. They did a phenomenal job, hence they won. Okay. The other teams also did a phenomenal job. It's just they happened to beat them. All right, so the tasks. So this is the second year we did the presentation task. Previous to this year, we would always just drill the teams in the science task, like why did you choose this instrument over this other? What were your trade-offs? What was your team structure? Why did your rover look like it does? All the decision factors. So last year we realized this is taking up too much time in the field, and it's hot, and the wind comes and blows the tents over, etc. So we decided to do a presentation task the same day that they have to weigh in. Each of the rovers have to stay within, I think, 50 kilograms, and any weight over that, it's 1 point per kilogram per task. So we weigh them in at the beginning. And instead of just weighing them in, now we also ask for a presentation on all their trade-offs, their team structure, their organization, etc. And it gives us a basic idea of what to expect in the field and how organized and prepared the teams were. These are two examples. One is Cornell and one is BYU. And there's no definitive guidelines for the task except for to tell us how your team is organized and why you choose what you chose. And each team did it a little bit different, but each of them were able to answer our questions and tell us the information we needed. So all the teams scored all the points on this task because they all accomplished the goals. Okay? One of the hard tasks that generally doesn't work out for teams is the astronaut assistance, and they have to drive their rover blinded over hills and gullies to reach an inside canyon area to find a quote-unquote downed astronaut. and give them a cargo packet. In addition, they have to drive and pick up the astronaut and bring them back. So they're given GPS coordinates, and they have to navigate to it, and they have to navigate with their cameras, and they can't see it. So because it's generally in a hill around the corner, a lot of the rovers don't make it around there, and there's about 5 different areas, and depending on how many that you're able to drop off, how many astronauts you're able to assist, depends on the number of points that you get. So, Andrew, do you remember how much York got this year? York, do you guys remember how many you guys did for the astronaut assistant? 0. Oh, 2 astronauts. Okay, yay. Yay. That's more than a lot of teams did. And this is an engineering task. I should mention I'm a science judge. Okay, another engineering task that was new this year, worked out pretty good, was the solar panel. The teams were not allowed to use any type of fluid spray or anything like that you wouldn't be able to use on Mars because of the extra mass or weight constraint that it would be just to take fluid to Mars just to clean off a solar panel. We did have a dust devil during the competition, but unfortunately it wasn't during anyone's competition of the solar panel cleaning, so it didn't benefit anyone because the dust devils clear off the solar panel on Mars. So this happens to be a picture of the Brigham Young University. What that is a bunch of cut up jean strips. I think they're glued to the edge of a beam, and then they have just a rotator pulley to clean it off. That costs them, all of it is used parts, including the jeans, and they did the best job on the solar panel cleaning task, and they spent hardly no money. So that's and it worked. It worked perfectly. So that's an idea of creativity when you don't have the resources. So I think this task actually was what bumped them up to second place, was the solar panel. Okay, the site survey task is a bunch of poles with symbols on them, and the rover can go to one place, see all 5 poles, and triangulate and give us the GPS location of them. The rover's not allowed to drive to all of the locations because we place them where the rovers can't physically get to, and so they have to use triangulation, and they have to use landmarks to take a survey of the area. So that's pretty straightforward. They just take the area and give us back GPS coordinates and the design and colors of the electrical tape on the 5-foot poles. And this is, this is BYU starting their site survey task. And I should mention that all of the teams drive the rovers blind, meaning they're in a tent and they can't see the rovers except for through whatever cameras they put on it. But they are allowed to have team members follow the rovers to take pictures of it, as long as the team members are not in the angle of view to give a scale size. The team members also assist in the unfortunate event that the rover tips over. They can pick it up. Okay, so another test is generally my favorite task, but everybody's accomplished it this year, so we'll change it, is the sample return task. The teams have to pick up a sample between 25 and 250 grams and give analysis on it. They have to also go to several sites and tell us why they chose that site for the best potential of life in the desert. And it can't be something obvious like a plant or manure, okay? It has to be just desert soil or etc. So they look at, they look for fluvial flows, signs of water, signs of pavement, soil crust, rocks with indolence in them, etc. And some of the teams have spectrometers on their rovers, so they can actually take a spectrum of the soil and see if there's any chlorophyll in it, indicating cyanobacteria. The methane, they can do methane. This team is York, and they brought a microscope. So some people bring microscopes, spectrometers, pH tests, you name it. And they have both an in situ and a lab component. So what we grade them on is we grade them on the questions that they can answer in our background material and the sites they chose and what they found. Even if they didn't find life, they can still make pretty good scores as long as they did their background research. So this is my favorite task, and it's usually the hardest one. Okay, so with that, that's the task this year. The overall scores were pretty close. They were all within like 55 points of each other, so that's really close. Each task is worth 100 points, so that's like half a task within each other. So the competition's getting really, really close, but everybody's doing a great job. And then I want to thank you and congratulate York. This happens to be an evolution of York's rover throughout the years. We have 2008, 2009, if you notice a huge difference in the size. So 2008, we had pretty rough terrain and some gullies, and a lot of rovers flipped over. And so if you notice, this is a wider chassis, a little bit higher, some ground clearance of the rocks, and the camera is on the mast. So 2009, it's the same wide base. That worked out for them with the cameras mounted here and then a flag. I think after they did the flag, other teams started doing the flag too, 2009. 2010, wider, flatter, the wheels are more durable, and then, so this is 2011. And this was their winning rover this year with the inflatable tires, the wide chassis, the maneuverable, what is it called, the rock and bogey system, I believe, and then the flag, and the camera's even higher, and they have the robotic arm for the sample return and the pinching of switches. Okay, with that, I would like to say that York has won the competition before, and has placed, I believe, every year that they've competed. And I want to congratulate them again from the judges and the Mars Society for their victory this year again, and we hope you'll return next year. So let's give them a call. And then do you want to set up your computer right here? Do you need this laser pointer? It's a 5.2.
Sure. Yeah, that'd be good. Thank you.
You're the engineer, I'm the IT.
I got dev support too.
All right, so do you guys want to extend or just duplicate it or whatever?
That's fine. That's fine here. Oh, that's too easy. Well, good morning. Thank you so much for having us again. It's one of the big advantages of winning the competition is just a chance to come to the Mars Society Convention, see all the great speakers, and I got a chance to kind of share our passion and the things that we do and why we do it. So before we kind of get into the whole why, what was the rover we built, and why did we build it that way, I just want to give everyone a bit of an introduction as to what the team is, how it works, how does this thing even come together. So the team itself is composed of varying numbers. It exists in a flux state between, say, 30 to 50 members throughout the school year. And we have a very big team, but obviously we couldn't bring everybody. So I'd just like to take just a quick moment and ask all the members that are currently here to just stand up. And if we could just give them a quick hand. Thank you. And if there are any questions, you are free to ask questions to any of us after as well. So how does our team work? So we have faculty advisors, we have student team leads, and then a whole bunch of team members, but our structure is broken down into even smaller sub-teams. So we have development teams, mechanical system teams, science teams, marketing teams, public relation, financing. So it takes a lot of effort and a lot of different skill sets to put together the rover team. And I believe that that's one of the things that makes the project so successful, is that this is something that involves not just engineering and not just science. So our team is composed of members from all faculties. So we have members from arts, members from science, from engineering, from computer science, and everyone kind of works together and brings their own skills and passions towards the project to truly make it a success. And the reason why we try to do this is because outreach is a really big deal to us. So we try to get out to the community as much as possible. And so we do career days. We teach kids how to drive the rover. And that's one of the neat features that we always like to say, that our rover is so simple, a kid could drive it. So it takes about 10 seconds for a kid to learn and about 5-6 minutes for an adult. And so we also like to obviously attend these conferences. Thank you so much for having us. And we have really strong recruitment campaigns. One of the big challenges for fielding a team is continuity. So a lot of the times a team will come by, they'll have one really strong member, and the next year it'll get weaker and weaker. But at York, we really try to make sure that every year we teach the members. So you don't need to know anything about building rovers. When you come on board, we teach you. And that kind of takes us to our workshop section. So our team puts on workshops throughout the year as well, where we teach technical skills such as microcontroller programming, as well as 3D modeling, how to make something. And I kind of wanted to include that quote because that's one of the biggest things about projects like this, is that technical skills certainly help, but it's the desire to want to make something that really makes the difference. So we definitely try to make people excited about Mars rovers, not just about building this Mars rover. And for our fundraising, as Heather mentioned, our funding varies. The majority of our funding does come from the university. We're extremely fortunate to have their support. We do also go out into corporate companies and we ask them for support. So Crosswing, which is a local robotics company, does sponsor us. But we are a student group, and I do want to say we do bake sales all year long. We have fantastic bakers, and that's actually one of the things you can join the team to do is, if you want to do bake sales and help us with that, you can do that. And they are delicious. And if anyone wants recipes, we have one of our excellent bakers over here. She'll be more than happy to share that with you after. So what is our goal? After competing in the competition for so many years, we wanted to push the envelope for ourselves too. When we came down to the design, we didn't just want to go and win. We wanted to design truly a modular and reliable rover platform. So a platform for developing rover systems. And this was meant specifically with the human exploration of space. So the question we're trying to answer is, if you're an astronaut and you're going to go to Mars, what kind of rover would you want to take with you? And that's kind of what started off our whole design process. So as usual, we have to do the same assessments. So we have to take consideration weight, which for URC is 50 kilograms for the mass. We come in at 49.9, so we try to make the most of it, as well as the terrain, time conditions. We have less than a year to put together the whole project, from idea to a competition rover. And we go through a process that every year improves and gets refined. This year we started competing also in the NASA Lunabotics Challenge held at the Kennedy Space Center. And that kind of exposed us to the NASA systems engineering approach, which we try to incorporate as much as we can. And so we go through macro design phases where we just kind of think of the big concepts, working to our micro design where we actually figure out the exact position, size, location of every screw, every bolt, every little wire. Everything about it is worked out ahead of time. Then we go into our fabrication. All the fabrication is done completely by students, some of them for the first time ever walking into a machine shop. And then finally we have to do a delivery, so we do systems integration, field testing, reiterative approaches to make sure that it's as reliable as it can possibly be out in the event. Because unlike, say like a current like Mars mission, sometimes they'll have a problem and it could have maybe a day, 2-3 days to figure it out. We only have 40 minutes to get a perfect score, and there are no second chances. So we have to try to have as much confidence in our hardware as possible. So this is a little bit of a sample of what our schedule is. So we have, this year we had 2 projects going concurrently. So we had Lunabotics, so we kind of have to have our macro design. These are sort of our milestone dates. So by middle of October, we've kind of figured out the concept that we want. By the end of December, we have blueprints that we can actually take into a machine shop. By the end of April, the rover is built, and then by May, we are ready to go compete. Now, this is a hopeful timeline. We obviously have a little bit of flex space in there. So we were also one of the teams, as Heather mentioned, that the night before are frantically trying to figure out some of those things. And so what was the whole result of our process? So this year we came up with the Ares MCR5, which stands for multi-configuration rover, 5 being the number of configurations. And the additional configuration that we have was for Lunabotics. And this is kind of what we were talking about when we said we wanted to have a platform. So we wanted to we boiled the elements of the rover down into the components that would make for a successful design, so we could treat other competitions as just an additional task. URC in itself is already extremely challenging. So we were able to look at NASA as just, oh, we have to build equipment for just one more task, so like an extra URC task. And it worked out quite well. And one of the principles that we have to try to abide in our design was MTTR, MTTF, and MTTC. This is the engineers talking. We love acronyms. So one of the big things that we always try to figure out is, what is the fastest that we can repair something? What is the fastest that we can change the configuration of the rover? And also, how long will it take? So we conduct studies to try to figure out how quickly we can do those things or how long it would take to fail. So an example for our repair is, there's a criteria that there are no components on the rover which should take more than 5 minutes to repair. So we can swap out anything from the entire suspension system to cameras or wheels or motors in under 5 minutes. And that's because if something goes wrong in the field, you need to be able to quickly address it and keep on working. So we come up with a design. We ended up got very close, exactly almost what we intended to build. And this is an example of the flexibility of our system. So this is us at NASA, and this is our lunar miner. You'll actually notice that the chassis is exactly the same, the wheel systems and so on, but it actually looks like a very different rover. And there are no components here that were manufactured just specially for this. So even the suspension, the motors and so on, it's kind of like a Lego system. So we can just put them in different places and then we have a different configuration altogether. In the end, we were able to come up with 8 unique configurations for the rover, so we could have lots of flexibility without having to increase the cost in development. So these are just a brief of our rover systems that we developed this year. So this year we came up with a chassis that was meant to apply a standard. So the chassis itself has lots of little holes along it. They're all standardized, so they're exactly 3 inches by 3 inches, and they have a 1/4 inch hole. And the reason for the 1/4 inch hole is because that's the most common screw size in the world. So the idea being that to reduce costs, we are taking advantage of that. The chassis is made so that if you want to attach anything to it, you just use that system and it will work. And we conduct things like stress analysis. Our chassis, the failure for it is about 2,000 pounds, which is a little excessive, but we are pretty rough on it sometimes. This is our new robotic arm that we designed this year. So traditionally, we've been using a Cartesian system, so X, Y, Z, and it's very simple for control. This year, we tried to do something that had a little bit more math, a little bit more technical expertise involved. And we also utilized a new system where we started incorporating carbon fiber into the design. So this enabled the arm to actually have a 50% weight reduction. So our arms traditionally were about 30 pounds. This year they came in under 15. And also, because the arm is so simple, it's very easy to repair, very easy to maintain and configure. So between competitions, our arms could change drastically in just a matter of minutes. In fact, for the science task, we had a failure minutes before the competition. We were able to reconfigure the arm and still get out there in time. And then that's the arm that was actually built, that was sent into the competition. This year we tried some new robotic systems. We tried something called the Canfield joint assembly. It's kind of like a carpal system, so it looks like a wrist. And again, this is also all made out of carbon fiber with acrylics, aluminum. So one of the big challenges we always have is weight, so we always try to make sure that we can maximize for those features. Our suspensions assembly, and this is where we really go off the deep end regards to, say, traditional Mars rovers that you guys have seen, because our suspension is actually inspired by Formula One racing. Now, you might be thinking, what does Formula One racing have to do with Mars rovers? Well, not a whole lot, as we know it right now, but we anticipate that once you actually get on the field, speed is an issue, and again, the ability to fix. So something that race teams do very well is, if a car crashes, if something breaks, within 17 seconds, they'll have it fixed and back out on the road. And if you're on Mars, you don't want a really long time for fixing things. So you want a system that can be high speed, adaptable, changeable, and so this is sort of where inspiration came from in there. We also experimented with some new materials this year. We started building all of our electronics enclosures and all of our geometry shapes out of a material called Lexan, which is the same things that you would use for motorcycle shields. So this thing is virtually unbreakable. So you could throw rocks at it, you could try to stab it, and all of our electronics still stay quite protected. And then comes the fabrication. So as I mentioned, everything is completely done by students. All of the pieces that you guys are about to see were completely machined by us. We started off in going to a machine shop, and we're learning as we go, so we actually have to figure out the position of all the holes and so on. We start machining the pieces. So this is Alex, and this is actually his first time in the machine shop, and so he's kind of learning as he goes along. We do all of our work on mills and lathes, but we also do hold a very high standard of precision. So all the pieces here are machined with plus or minus 1/1000 or 2,000th of an inch, so that we can have multiple pieces, and just if something breaks, it's easy to swap out. We made close to 600 unique pieces this year over the course of about 2 to 3 months. And this is what the rover looks like on a table before it came together. So for the development, I'm not going to go into too much detail right now, but I do have Glenn Brissett, who is our lead developer, and he'll be more than happy to answer any questions after. So for development, we write all of our own software. Traditionally, we've also been building all of our microcontrollers. This year, we kind of started stepping a little bit away from that, again, for cost and ability to be competitive. So we utilize an onboard computer. We have a 900 megahertz, which is meant to address the terrain issues, so you can go a little bit further and see around mountains. But we also try to utilize a very strong communication interface, so we have our own protocols that we write, so we have complete control. And what this means is if there is a wire anywhere on the rover that is disconnected or not functioning, we know where that wire is. So if there's an issue, we can address it very quickly. Again, that downtime needs to be quite low. And our graphical user interface, which I'll kind of discuss a little bit, which is one of the big advantages that we have in operating the rover. So for development, we utilize our onboard computers, Wi-Fi. So this is the same thing that you would have, say, like in a home computer, just a little more compact. So we run Linux, and we try to take advantage of as much technology that is available out there. So if we don't need to develop it ourselves, we certainly don't. But this is something that we actually did come up with this year. So our entire system is built on a daisy chain. So we can add as many motors as we need as we go along. So if you had, say, a 4-wheeled rover and you wanted to add another 2 wheels, another 2 motors, our system is built exactly for that. So we can change the configuration to do that. So we have high power and low power controllers, so 12 volts and 24. And these are all exactly identical. The only difference is we assign them different IDs, and then we can just swap it out. If something in the field breaks, we take it out, we put a new one, turn it back on, it's like nothing ever happened. So this is it almost feels like an out-of-the-box system, but it was actually completely custom built and designed by our students. And all the systems also have their own enclosure. So there's a massive enclosure for the collective systems and also an individual enclosure. And this is because dust out in the desert is a huge issue. This year we had a massive sandstorm that completely ripped our boxes open. But if it were not for their own individual enclosures, our rover would have definitely been fried. And some of the other rovers did have that problem. So our communications, this has been going on for 5 years. So I don't want to give the impression that we came up with this in our spare time between classes. And the rover actually has its own internet system. So the rover is built on a server and client system. So again, we can add more computers, more devices, and the flexibility is there. And this is just, again, meant to simplify that whole process where we're trying to make it as adaptable and flexible, because to us, that's the key to winning designs. So a basic outline of how the system will work is we have our base station, a little wireless connection. It goes to an onboard computer onboard the rover, which could be 1 or 2. And then we can just start adding devices as we need. So pen and tilt controllers, missile launchers, temperature power monitors, arm controllers, you know, whatever your fancy is, we just plug it in and go for it. This is our GUI, and our GUI is inspired by video games, as you can probably see. And this is an actual image of what you would see with the rover. So we have tilt sensors that are built in, so while you're driving, you have no depth perception. So you actually need to rely on your instruments to know if you're going up, if you're going down. You're so low to the ground that it feels so unnatural. We monitor link quality continuously, power levels, connection to different devices. So again, if there's a motor anywhere that disconnects, it'll alert us right away, as well as a compass, so that when we're navigating, the way that the structure of the command center is, the navigator will say heading 326. So the pilot will just put in that heading and he'll be monitoring the system all along. So so we can be very efficient with how we navigate the desert. This is all possible by completely new technology. So this year we can add H.264 video compression, which enables us to get high definition at less bandwidth than it would take for a USB camera. So this is something that's just completely new. This came 3 months before the competition started. This is when the technology came out. And again, we were able to implement this because of our flexible system. This year for the surveying, we tried something a little bit different. Traditional surveying, as you guys have probably seen sometimes on the roads, there'll be a guy standing, has something that kind of looks like a telescope. He'll point to something and then try to measure it, figure out angles, and get the information back. York has a very strong surveying program and surveying students. So this year we switched to something called photogrammetry-based surveying. And what this essentially does is we go out into the field, we'll take a picture, and we'll have, say, 3 known points. So if you don't have those points, so you drive over to 3 places, record the GPS coordinates, and then all you have to do is take a picture. The more pictures you take, the higher the resolution becomes. So an example here, this is our campus. This is our science building. We have an observation here, an observation there, and several unknowns. So just from the picture alone, we can infer the exact position of these points, and the more pictures we have, the higher the accuracy. Our absolute maximum limit is the centimeter level. So we can tell where things are within plus or minus 5-6 centimeters, just from the images alone. And then comes the science. York has a very strong science team, and there's, again, an entire team that works all year on being able to answer all of Heather's questions, which is probably one of the more difficult parts of the challenge for sure. It's definitely the part that we work the hardest at. And we have a very simplified strategy, not quite as complex as many of the systems we've heard about this weekend. But the things that we generally look for are cyanobacteria, desert varnish, lichen. And we utilize, for the majority, optical instruments. So we have an onboard spectrometer, and as well as pH sensors, high-resolution cameras, so we can take very up-close shots and be able to resolve the detail. The highest resolution that we can get is about 2-3 millimeters, so we can actually resolve the granularity of some of the samples that we look. So depending on the kind of sandstone that we're looking at, we can kind of try to tell what kind of sandstone it is and try to get at least some of the information back to us. All of our selection of our sites is based on initially visual clues. So we look for signs of waters like fluvial folds, things that would cut through, desert crust. And again, these are only things that are possible because of our high resolution camera systems, as well as green. If you see green, to us that means life. So that's one of the big things that we're always kind of keeping an eye out for. But because we need to be again, answer those very tough questions from Heather, we try to come up with a lot of science to back it up. So we do have an onboard spectrometer, and we calibrate it so we can detect wavelengths of chlorophyll-based pigments. And so this is an example of a spectra that we would get live in the field of a particular sample. This was where we thought we found life last year. So in this particular instance, we figured that there was a very high probability. The science team said, okay, let's bring that sample back. And then at the base station is where they do all the additional analysis. This year in the rover too, we also added some analysis of the soil, so we could check for the pH, electroconductivity, as well as the moisture. And we tried a methane detector. Unfortunately, the concentrations were a little too low to make any reasonable conclusions from the data we received, but it was still a really good experiment for York, and definitely a direction that we hope to continue in the future. So that pretty much concludes. I want to thank, again, the Mars Society for continuing to put together this event. It's a fantastic experience for everyone involved. It's definitely been life-changing for me, as well as all of the other teams. And if there's any questions, we'd be more than happy to take them.
Before we do questions, I'd also like to recognize John Barenka here in the second row, who's also a science judge and is very critical for the science tasks getting completed and judging them. So if you'd also like to come up here for questions, you're welcome to, or to answer questions. Okay, so are there any questions for either myself or York? Yes. Right there with the hand still up.
The scores seem to be in the 220 to 280 sort of range. How many tasks were there? You said there was 100-point possible, so were there 5 tasks?
There are 5 tasks. So the presentation task was 100, and everybody got perfect on that because they could all answer our questions, and they were done very well. The other tasks ranged from probably 0 points, maybe 10, probably 0 actually, up to maybe 80, depending on how well they did.
How many of the students involved are FIRST Robotics alumni?
I have no idea. How about your team?
So far, we've traditionally had 1 or 2 students. A lot of FIRST Robotics students are starting to come. They're finding out about our program. They're coming to York because of it. So I think so far we've had 1 student, but this year at a high school fair, there were at least 7 students that had chosen York and were from FIRST Robotics specifically to join the Rover team. So there is a link that's starting to develop, and definitely something we will want to capitalize on.
Thank you. Hey, any other? Oh, yeah, back there.
Yeah, I'm just curious about the interaction with the NASA robotics program. Was this year, I think you said, was the first time you did both, and I'm curious whether competing concurrently with 2 different programs, is that additive or is it distracting or is it, how did that affect your progress?
Well, it was definitely a challenge, just because the criteria is so starkly different from NASA to URC. But again, our strategy was that we believe we could develop a platform that was flexible in and of itself because the basic elements required to fulfill the tasks were equal. So your knowledge, your software had to operate in roughly the same way, your hardware needed to have roughly the same kind of flexibility and adaptability for it. So the biggest challenge for us was really just trying to come up with a system that could meet multiple criteria at the same time. So the challenge was really just that, was trying to figure out how to kind of meet it in the middle. And we were just very lucky that we had a team that was able to, everybody work together and come up with the ideas to solve it. NASA also put a lot of emphasis on the design process. So I would say that actually that was probably the biggest challenge, was coming up with all of the proper documentation. NASA loves their documentation. So this year, that was definitely the only thing I would say was a bit of a strain, but other than that, it was just a next evolution from URC for us.
And how did you do in the NASA competition?
I believe our final ranking was 18th out of 58. But to give an idea of the event itself, for the competition, for the mining part, out of 60 teams from all over the world, only 13 teams were able to qualify or even get working at all. The regolith is an extremely difficult material to work in, so it was definitely quite challenging. And these are some top-notch universities. So for our first showing, we were very satisfied. We took it as a learning experience, and we will definitely be back this year, hopefully to repeat our success in URC in other places.
Question to the York team. Do you have any suggestions on how the Mars competition could be made more interesting or improved?
I think the Mars competition itself is extremely challenging as it is. Most of us struggle, as Heather pointed out. Some teams get 0 points in the tasks. It may seem trivial, but it actually is quite difficult. I would ask them to make it a bit easier, but that's not going to happen. But in terms of the improvement, I think just more public outreach. There's a lot of universities that don't know about it, but that kind of goes for a lot of the other competitions. So I wouldn't say necessarily that the competition, but perhaps Mars Society, or if there's any faculty members in the audience or students, is take this information back to your university. You don't need to have a huge budget to do this. You need to have all the expertise. If you got the passion and you want to go out there and do it, you can do it. And the Mars Society has actually been really fantastic at just enabling teams to get that done.
Artificial intelligence. Once you've found a good route to go, can you have your roll out and return automatically and find a route back automatically?
Repeat that, please.
He was asking if our robot has any AI capabilities, so like auto navigation or so on. For Lunabotics, we had some. It was a benefit there because you could get points for having that. So we had some basic semi-autonomy, so the rover could drive over across obstacles or come back across the obstacles by itself. But for URC, we chose not to implement that because the desert conditions are so incredibly unpredictable, and in the 8 months we did not feel that we had the time to develop those capabilities. But that's definitely the direction that the team is going into. So part of the architecture that we were demonstrating was built that way specifically so we could address in the future AI concerns. So it's definitely something that we're looking into.
Okay, go ahead.
You said you were able to swap out modules for, say, controlling a certain wheel or whatever. How did you tell the new module what it was controlling if it was all modular?
I'm going to pass that over to our software expert.
Thank you. We don't necessarily need to tell it's controlling something differently. We use two different kinds of modules, one's for high power and low power. So we pick the proper module, and then we can even scan the system to find the new ID of the one that we've replaced to. So we just look for a number in the system. It looks kind of like an IP system that we've made for this. So we scan that, we find the new one that's not already assigned to anything else, and then we can just add just that number into the code. And it takes us, we've done it in the field in about 30 seconds if we have to. Most of the time is spent just changing the wires on this thing. Very little time is done in software.
Yeah.
Who pays for the team members to come to the desert?
The teams have to raise that funding, and sometimes it's out of pocket. So I know, I think the first year, one of the teams came, I think they made $300 total is what they had to work with. And so they went and begged and borrowed to the university, and I think they got $500 for travel to come down. So a lot of them, a lot of the students put a lot of their passion, their time, and sometimes their money into this competition, which is unfortunate. We're hoping to get some sponsorship so that we could at least allow some of the funding. But one aspect of the teams is also fundraising and promotion. So, I mean, York has done a great job, and I'll let them expand on that.
We're very fortunate at York because we've been doing this for so long. We can always get that support. This year, we were able to raise $44,000. $20,000 of that was actually promised to us by the dean. So as we were getting kind of near the end of the competition, we were having some funding issues. So he was able to fund all of our travel costs. So this year, the team hasn't had to pay anything out of pocket. We've been able to just mostly get by on our sponsorship.
Do you have any problem getting the rover through custom?
We don't have any problems except for some weird looks when they ask us where are you going, and we're saying we're going to go compete with our rover, and then they look at us weird for a couple of seconds. But for the most part, they just ask us, you guys had anything illegal in there? Like, no, sir, just a couple of nerds heading for some robots. But the Polish team, I know that they definitely have some concerns there because it costs them almost as much to build a rover as it does to ship it over. So they have to go through customs, ship it internationally. So the international team, especially overseas, have a lot of issues with that.
Also with Poland, on their first year, their rover showed up broken. Like they had to, I think there were 3 guys, and their first year, I mean, it was basically like the first day, they were just trying to reassemble their broken rover. And then the other thing is the Polish team, I think it's like 220, is it 220 hertz is illegal? No, is the one that you use in Poland, but it's illegal in the US. A 900 is the one that you use in US, but it's illegal in Poland. And so I know that there's also their telecommunications has to be adjusted, but mainly their rover shipment is thousands of dollars. It's really expensive. But with Poland, they did very well, and they were greeted by the prime minister when they got off the plane last year. And they did win the competition last year. Okay, any other questions? Yeah.
Are there boundaries to the amount of time you're allotted to assign the rover? Or?
No, we put out the rules, and hopefully in September, but in generally, usually they get out October. But September, October timeframe, and there's, I think, January, you have to have some type of paperwork in, and April, I think you have to have final designs, and into May, beginning of June is the competition. So the only time straight to the milestones that you have, but there's not like hourly time or anything like that, no. Okay. The one back there, and then that one, and then here. Okay.
You said it was mostly engineering students on your team. What is the breakdown of like majors, concentrations, focus of students?
Yeah, so it's getting a lot better. It used to be like no science, and I heard the thing, well, we're an engineering school. We don't know any science. I don't care. If you're an engineering school, you should know science. So now they generally have at least 2 or 3 scientists on their team. If there's a team of, and they generally also have more women as well, both. So the teams are pretty diverse right now, and I would say maybe 60 to 80% engineering and 20% science, but it's different per team, per university. And sometimes it's the engineering students that have to learn the science, but I'll let York answer that for their specific team.
For our team, in terms of disciplines, we have, I would put the breakdown at about 40 to 50% being pure engineering majors, so computer engineers, space engineers, surveying engineers. And the remainder breakdown goes into biology, so we have about 10-15% of the team is purely from the biological sciences, and then another 10-15% is from physics and astronomy, and then the remainder kind of becomes a mishmash of majors. So we have people from the humanities, from technology programs, from various different facets of York. So it's definitely very, very diverse, and again, one of the things that make for the team to be so successful.
You had a question? Yeah, so some are 30 minutes and some are 40 minutes. So the sample return is 40 minutes to be in the field, 30 minutes analysis, 15-minute briefing. The site survey is 30 minutes in the field, 15 minutes to analyze your numbers, and you give us a piece of paper. Engineering, what is your time limit? It's about the same? Okay, engineering's about the same, 30 minutes and 40 minutes on the field. And all the tasks have either a 20-minute setup time or 25-minute setup time, depending on the task and the year and the number of people competing.
How long does the total competition take?
So we run it over 2 days, 3 days. The first day is the initial briefing, the driving to the MDRS, the weigh-in of the rovers, and the presentation tasks. The following 2 days are the field competitive tasks. So all of the field tasks, so that's 4 of the 5, are done over 2 days. And you had a question?
I'm curious, this is a kind of a unique competition because it integrates the science and engineering. I know there's a lot of different engineering competitions out there, and I was wondering if part of the reason you don't have more teams competing right now is just because there aren't science competitions that focus on like field demonstration of science, and I'm wondering if like how you can sort of broaden the field to make the science component more interesting to scientists that want to get out there and do stuff.
Yeah, that's a good point. I think a lot of it we've just relied on the universities kind of campaigning for scientists, and I think that was like a pretty hard hit for everyone on year number 2 when they almost all of them failed the science task because they couldn't answer the questions. So at year 3, almost everybody had a science member on it. But other than the universities campaigning, I'm not for sure. We could get the word out more in general on the competition and maybe put a better description on it. Yeah, you're right. We probably could. The camera person?
Yeah, the gentleman standing, what was his name and job again?
John Baranka, he's a lead science judge.
Did he have any comment
Yes,
about
he did.
the judging?
Thank you, John.
I guess a comment that I have, first of all, is it's amazing to see how much these students do with such a small amount of resources many times. And the thing I think that's really important is the repeat people really do show how much they have learned and what the experience has done for them as they come each year. As Heather said, that at first the rovers would just barely start or wouldn't run at all or whatever the case, and now we've got very, very, very top technology types of rovers, as you probably could see when they were described on the phone, or on the screen. So don't be afraid if there's anybody in here who want to participate in it because it's a growing experience, and it's something that will make a difference in what you do later on.
Was there one more thank you, John. Was there one more question?
Yeah, it was just since York is in Canada and you've got the CBC, has anyone at York approached, and since it's a competition and you can win and you have won, if you had anybody from the CBC sort of interested in sort of following along your process and then producing a, you know, like an hour or half-hour long show about your project.
We've not had that kind of attention to us. We do try very hard to have lots of media outreach. So we have our website, Facebook, Twitter, and we try to get videos out as much as we can. The CBC does come by and cover us. In fact, they're covering us today. So back in Canada, they are kind of talking about the rover and what the rover has done and its successes so far. But in terms of that kind of content, I don't think there's been anything in the works so far. Not that we're opposed to it. More TV time would be fantastic.
Okay, so I think we're out of time. If you have any questions, if you could approach us later in the afternoon. Thank you very much.
Okay, now we're going to break for lunch. Be back at 1 o'clock, I believe.